what I would like to present today is a talk that I was giving on Monday at the British Neuroscience Association. So shamelessly kind of using material from earlier today for a different purpose. But I hope that it will be interesting for you nevertheless. It is about instability in deep learning, which is a project that I have been working on together with Ollie Turnbull in the spare time that he could save from some other projects. And let's kick off by just discussing what instability in deep learning actually is. So you might already recognize this slide because I've used a very similar slide maybe a year ago in my talk about generative adversarial networks. But if you don't recognize it, don't worry. It's all the information is coming now. So instability is an effect that happens whenever a small input change causes a large change to the output. Now, okay, let's make it less abstract. Within AI, it's most studied in machine vision as adversarial examples. So we will be talking about adversarial examples, and one of those is right at the bottom of the screen. So what that figure is showing you is that on the left we have the original picture of a pig, and then there is something that looks like noise, but it is actually very, very carefully crafted. And a very faint projection of that is added to the original picture of the pig. The faintness is noted by the 0.005. So all those pixels are kind of 200 times kind of decreased in their brightness, and then superimposed on the pig picture. And immediately the machine vision system classifies the picture as an airliner rather than a pig. And this is quite a big problem because people can't detect that, and people find this very counterintuitive. So the reason why we talk about, or why this talk is about deep learning, is because most of the machine vision systems these days are deep learning systems. And yes, that is basically the reason. But what I will be arguing for throughout this talk is that it is not about the deep learning systems, but it's about a general kind of way how visual world works. Okay, so these adversarial examples, as I said, are very tiny changes to the picture, but they are very carefully crafted, and it takes a very long time to find a particular pattern to superimpose in this way that does confuse the machine vision system in such a way. And they almost always exist while being very difficult to find. The very important thing to note about this is that this is not just bad performance of the machine vision system. These examples seem to be unavoidable if the system is meant to be accurate. So overall, a system that makes this sort of mistake, or according to us humans, it's a mistake, the system that makes this mistake is going to be more accurate than a system that we create in a way that it is stable and it won't be making mistakes like this. Okay, any questions on this so far, on the background? Yes? No? Everyone happy? Perfect. So this slide is about a piece of research that I found tremendously fascinating. Is slightly tangential to what I'm talking about, but I'm sure you will find it very fascinating as well. So this paper that came out last year, I think, is actually showing that these adversarial examples, or those patterns that look like noise to us, are actually statistically significant features, which is really fascinating because if we interpret it in perhaps well, maybe stretch it a little bit. Then what this is telling us is that those are actual patterns that our brain cannot see, but are valid patterns of the objects that the resulting image is classified as. Which I do find very fascinating. And it might be that just our visual system is just not built to detect these, but deep learning does detect them. Now, why does this matter? This matters because it's not just about two-dimensional images that are fed into some sort of automated system, but you can also create objects that you can walk around the real world, and they will be misclassified in a terrible way. So what we see on the top of the slide is a 3D printed turtle that gets consistently classified as a rifle by a machine vision system. Now, the texture of the 3D printed turtle is modified, but it still looks very much like a turtle to us. So if you think about a lot of security applications of deep learning, for instance, detecting that there's someone running around with a gun in a tube, then this whole use of machine vision can be completely invalidated by someone walking around a tube with this turtle, raising alarm everywhere, and as a result, the whole application is rendered completely useless. The other example that I'm showing here is a modified stop sign that gets interpreted as a speed limit. Now, this is obviously a huge problem for autonomous cars, for instance, because instead of stopping at a junction, the cars will just slow down, which can obviously have very bad consequences. And the worst thing about this is that this is impossible to detect by humans. We do not see it as what it gets classified as. So if there are alarms of someone carrying a gun in a tube, and police is called there, they will just walk past the guy with the turtle and not realize what is going on at all. So they are very difficult to counter these examples. And so far, attempts at fixing this issue lead to just simply an arms race. As machine vision systems are better at finding these instabilities and preventing them, the systems that generate these examples, the adversarial examples, are also constantly getting better. And the last problem that I see with this, and why this really matters, is that the existence of these examples seriously undermines public trust in AI. And I think that we are all clear on that there are some very useful and beneficial uses of AI for the society. But because people do not understand this, they are uncomfortable with using these systems, and it may actually end up with those systems not being applied where they would have been very, very beneficial. Okay, so that is why it matters. Now, the past research onto this topic consists of mainly two papers. The one on the left is showing that the reason why the adversarial examples exist is the underlying uncertainties about classifications of objects, which is interesting, but we thought that it is even something more general than that. The paper on the right describes the existence of the adversarial examples as a result of rectified linear units based convolutional neural networks, which is a mouthful. And the only important thing about it is that is the most prevalent technology across machine vision. So the statement that I will be making here is slightly stronger and compatible with both of these pieces of research, and that is that it is a general feature of how visual world works. So how does the visual world work? The way how we understand this is that there are some semantic features, such as dog. And there is one very important aspect of these semantic features, and that is that they are translationally invariant. What I mean by that is that dog is still a dog wherever it is in a picture. So as you translate it across the picture, it is still a dog. Even when the dog is upside down, it is still a dog. Now, the other thing that we have are visual features. So the semantic features get projected into an image that we perceive with our eyes or that we record on a camera chip through kind of rendering of those objects into visual features that are also translational invariant. So the visual features are sort of corners, edges, spots, and things like that, which again, corner is a corner wherever it is on the image. But the semantic concept, the object, gets rendered into image through use of these visual features. And then we end up with image, which is not translationally invariant anymore. Image has specific locations of everything, and it is in some sense fixed. Okay, so if everyone's happy with that, I will carry on. If not, let me know. Now, how does visual object recognition work in AI and in animals is the question. And this is potentially the only slide that contains any neuroscience. So don't worry, it's not going to get heavier than this. What we know about convolutional neural networks, that are the main machine vision approach these days, is that they are essentially hierarchical pattern detectors. So they detect low-level features such as edges, then more complex in the next layer and more complex until they identify semantic features from those visual features that are detected across the image. So in some sense, it is just inversion of what I was describing on the previous slide. It is the same, it is essentially our understanding of how image is generated, and we take it in reverse to infer what actually is on the image from the image itself. Now, this is very similar to how we understand human vision. One of the things that is very well studied within neuroscience is the visual cortex, and what we know is that already actually on the retina there are some pattern detectors, and also in the visual cortex gradually more complex patterns are being detected from the image until a semantic concept is identified. And what I'm showing you on the far right-hand side is actually quite fascinating. I mean, it is in some sense fairly obvious, but what that plot is showing you is that the representations that the machine vision systems get in low levels of the system are very highly correlated with the representations that are in lower level of human visual cortex when the machine vision system and the human is exposed to the same image. And this goes further. The higher levels of a machine vision system are better aligned again with kind of later visual areas in human cortex. So the way how we understand visual processing in humans is very well aligned with actually how we do visual processing in machine vision systems. Now, to make my argument, I will have to start with discussing the mathematical properties of the representations that we are dealing with. So first we need to start with the image. Image is an extremely high dimensional continuous space. The way how we understand images in machine vision is that each pixel is an independent dimension. And actually further than that, it has 3 dimensions in every pixel because there's RGB components. So when we look at a machine vision system such as ResNet 50, which is kind of a gold standard machine vision system these days, or for quite a while already, the images that are fed to that system are 224 by 224 pixels times RGB, which results in 150,528 dimensions of continuous values. And that is a very complicated space to think about and reason about, right? But let's leave that for later. I would just what I want you to remember is that it is extremely high dimensional and continuous space. Now, the other important space that we have are the features themselves, the visual features. In case of ResNet 50, this is 64 features of 7 by 7 pixels. So that is, I mean, 49 dimensions is very high dimensionality, and I still find it difficult to think about it. But it is far lower dimensional than the image itself. And it is continuous again. And now, what is very important is that these features are translationally invariant. So wherever the feature is in the image, it is still the same feature. Next, we have semantic features. And this is a completely different type of space. It is a categorical space. So something is a dog or a cat. It is not somewhere in the space between a dog and a cat, or at least that is how we understand the world. In case of ResNet 50, we have 1,000 categories that the image can be classified as. And again, these are translationally invariant. Okay, so how do we study the problem? So the conceptualization of the problem that we've developed with Oli, we've really simplified the problem as much as we could, so we can tackle the problem with our limited human brains that can't deal with 150,000 dimensions. So we have created this toy system or a model that uses 3 black and white pixels, so that is 3-dimensional image. And the very nice thing is that we can not only display it as 3 pixels, but we can also display that as a 3-dimensional space, and that is very useful for reasoning about what is actually going on. Then we have visual features that are lower dimensional continuous space and is translationally invariant. We have 2 features of 2 pixels each, and that we are detecting these features in the original 3 pixel image. So very, very, very simplified. And in the end, we only have 2 semantic features that are categorical and translationally invariant. So what have we found? The first thing is that when you project these semantic categories back into the image space, which is what I'm showing you on those plots here, each of these plots is showing you essentially the space that are described in each of these plots are essentially all of the possible images that you can have with that very simplified 3-pixel image. Yeah. So you can have all combinations of the pixel values will be a point in that space. And now what I'm showing you are the 2 semantic features that we used and how they are projected into the image space. What we find is that as long as the semantic features are translationally invariant categories and the visual features are lower dimensional and translationally invariant images that are detected in the original image space, we get very complex boundaries between those semantic features. It is not a nice transition. It is very complex, and it gets more and more complex the more dimensions you have in the image space and the more semantic categories you have. So in this case, you see the 2 semantic features. They actually are volumes that slot into each other in this very counterintuitive way, which is a reason for instability. There are no reasonable transitions. I mean, there are possibly some reasonable transitions between semantic features, but mostly it is quite choppy and quite counterintuitive when we think about it in the original image space. The other thing that we are consistently finding is that while we are finding the instability, we can find it almost always. The instability is extremely unlikely, or what it means really is very, very difficult to find. And the reason why that is happening is that the regions of instability are generally lower dimensional than the original image. Now, let me unpack that for you. So on these plots, what I'm showing you is an image space that is drawn only for 2 pixels to make it really simple. So we have 1 pixel on x-axis and the other pixel on y-axis. Any image, 2 pixel image, will be a point in that space. And if we have a region of instability that is 2-dimensional, it is fairly easy to find it. Just think about picking random points in the space, and you will eventually hit the region of instability. But if you have a lower dimensional region of instability, such as on the right-hand side, where I'm showing you one-dimensional region of instability, just a line, that is obviously much, much, much more difficult to find because it is a much smaller object in that space. Okay, I will start wrapping up here by saying that instability, as far as we can see, is a feature of the visual world. We are yet to formally prove that, but we are constantly seeing that in our experiments in the simplified toy model that I've shown you before. And what seems to be really crucial for the instability is the translational invariance, as I mentioned before, and the differences in the very dramatic differences in the dimensionality of the different spaces, with, in the end, having categories as opposed to continuous space. A second thing that we are consistently finding is that the instability is improbable. And while it exists, it is difficult to find. And this brings me to a slightly more upbeat message, that the solutions to this problem actually do exist. And the solution, in my opinion, is really rooted in my previous point, that it is very difficult to find them. Finding those unstable points requires a lot of computation and requires a lot of attempts at finding that spot. And this can only be done for high throughput systems, such as an API that is exposed to the public, and people can try upload 100,000 images and will get results from the API and can keep looking for the regions of instability. But if we have a throttle system, such as is an API that is limited to only allow you to do 10 queries per day, then it will not be possible to find a region of instability. Well, I mean, it will be possible to be precise, but it will be extremely, extremely unlikely that anyone will be able to find such a region, such an example, adversarial example, that will confuse the machine vision system in a catastrophic way. Now, this also has, unfortunately, bad implications for kind of openness and what kind of the machine vision community or machine learning community in general really likes, and it is publishing the models, publishing the data that has been used. And that can't be done if we want to keep the system protected from instabilities and adversarial attacks, such as I've shown before. And a very useful thing is that identical models that will be trained on slightly different data sets will have instabilities in slightly different areas. So it might be the case that we can publish our machine vision model, but we can't actually say what exact data we have used to train it, if we want to protect that machine vision system from adversarial attacks. And that unfortunately has quite bad impact on transparency and kind of being open with the public of about what we have done and how we have done. Okay, and that is thank you for your attention, and mainly to Oli because he has done a lot of work on this, and also the rest of the team that has had kind of critical but very constructive input.